doing the this is the second class, and we will be doing the Opamp circuits only. And in the past few years question paper I was going through, and I saw that mostly the questions that are there are not that difficult. They either you will have to, like, obviously in Opamp questions you will have to go through uh, you have to use KCL KVL equations, so please make sure your network theory is good. Okay, network theory concepts are needed. So you will be obviously using KCL KVL superposition in Opamp's question. And also very important, if they want to make Opamp question a bit difficult, they can put transient analysis, right? So these two, please make sure that you are well aware of. Mostly transient analysis will use capacitors, switches, like that. Okay, and how more they what more they can do with Opamps? So what more they can do with Opamps? They can give you filter questions. So be careful with the filter questions. Now these filter questions, like Opamp circuit can be modeled in low pass filter, high pass, band stop. Okay. Now from these filter questions, again they can club with network theory, and they can ask you Q factor, quality factor. They can ask you that, or they will ask you about frequencies, upper cutoff, lower cutoff, bandwidth. These kind of questions may come. Okay, so they can club with filters and this. Now here they can do another clubbing, that is with the control systems, the concept of Bode plot. So they can give you Bode plots, and we had seen in the last class, right? So they can give you Bode plots, and from here you have to derive the transfer function. Okay, so now the question can be framed as, they have given you a Bode plot, okay, and they will ask you upper cutoff, lower cutoff, and stuff like that, even quality factor. So from Bode plot you will have to go this way, right? They can also ask you questions about damping ratio also, right? That can actually give you an idea about whether the system is under damped, over damped, critically damped. All these kind of questions can be framed. Okay, because once you have a second order system using an Opamp, that second order system can behave as a filter, it can behave as an oscillator, right? So depending on what purpose is actually whatever the values of the parameters are. So if you see, if you want to solve one question, you actually need to have a conceptual idea about at least 3 subjects, especially network, signal, analog, and control are clubbed together. Okay, these are normally, they can be, it's easier to frame questions which have which seek the knowledge of these 4. Okay, so you see, you need to take Laplace transforms in the question, right? The If you want to use Laplace transform, because once you enter the S domain, then you enter the transform theory. So you use signals also. The input can be a unit step input, the input can be a unit impulse input. So you need to know about that. So please be careful, don't leave any one of these. If you leave any one of these, the other 3 you might not be able to solve, even if you have practiced it. You understand? So please practice these 4 very well for your GATE exam. So okay, so with this, let me start with the first question. This is a GATE instrumentation 2016 question. It's a sort of easy question only. So you see the, okay, so what kind of feedback is this? You see there is a capacitor also in connected across the positive, making it look like a positive feedback, and there is a the resistors also. But this is a negative feedback system, because these are, the resistors follow Ohm's law, right? Strict Ohm's law. So this is a negative feedback system. Okay. Now depending upon your frequency, this feedback will be either open or close, and then the circuit may oscillate at some point, or it may not oscillate at some point. That will be decided. That is a different thing. But with first look, you see that this is connected to the negative terminal. There is a negative feedback system, and we can apply virtual ground concept. Okay. Now, what is the question asked? So the question is asked, in the circuit given below, op-amp is ideal. The input Vx is a sinusoid. Okay. The input Vx is here. Input Vx is sinusoid. And ensure that Vx is equals to Vy. So if you ensure that Vx equals to Vy, what will be the value of Cn? Okay. So simply you apply virtual ground concept. Okay. So this is Vx, this is, so Vout, and now you can find the transfer function from here, right? So this is also Vy, right? And you have one equation with Vy and Vout. So please start solving. Vy by 1 plus Vy minus Vout by 10 is equals to 0, right? So what will we get? 11 11 times Vy is equals to, is this fine? 11 times Vy equals to Vout is your first equation. Now the second equation will be Vy, this current is 0, right? Because Vx is equals to Vy, so there is 0 current flowing through that branch, and therefore we can write the KCL equation as Vy into 1 nanofarad. So I am writing it as, let me say this is C. 1 nanofarad is C. So Vy into Xc, okay, plus Vy minus Vout into Xcn equals to 0, right? And now you can now you can again put, in terms of Vy you can put Vout, and then so what we will do, we'll change this to Vy Xc plus Vy minus 11 times Vy into Xcn equals to 0, right? So Vy will cancel out. So Xc equals to 12 times, 10 times. Xc equals to 10 times Xcn, and therefore Xcn will be Xc upon 10. Now what is Xc? Xc was 1 by omega c, and what is Xcn? It is 1 by omega Cn. So omega will anyways cancel out, right? So therefore your omega Cn, so I have done a mistake. I think this will be all division. So if I write Xc, I should divide by this. So Vy upon, this is upon, this is upon, this is upon, and yes, so this will be Xcn and this will be Xc. So Xc is 1 upon omega c and Xcn is 1 upon omega Cn, and therefore Cn is nothing but C upon 10. Right? So this was 1 nanofarad upon 10, that is 0.1 nanofarad is your answer. Now, did you understand what I have done? So Xc, when we write, Xc is reactance, which is 1 by omega c. So this is having the units of ohms, and therefore the current will be voltage divided by Xc, right? But if you write in terms of C, then this will be what? I is equals to V upon 1 by omega c and V into omega c. Okay. So admittance, capacitance is nothing but admittance, behaves like an admittance, and reactance will behave as a resistance, right? So yeah, so this was a simple question, and the answer is this. One thing which can go wrong is if this is asked as a numerical answer type, which normally these kind of questions are numerical answer type, and you see it is written as picofarad. So if I now write 0.1 in my answer, this is wrong. So how much picofarad is this? 100 picofarad. The answer was 0.1 nanofarad. So how much picofarad it is? It is 100 picofarad. Okay. So please, I am giving you a minute. Please resolve this question before we go ahead. Please let me know once you are done. Okay, then I will proceed.
Hello,
Yes, Chandrasekhar.
ma'am. How it is negative feedback because a capacitor is also
Yeah,
connected
so
in.
normally in DC condition, what will happen? Capacitor will be open circuit, right?
Yes, ma'am.
So when we are applying virtual ground concept, normally when we are looking into the gain, it is the DC gain that we look into, right? So you have to take that condition, apply it, have a relationship with Vx and Vy. The capacitor will be open or short, it will apply a feedback according to the frequency that you apply. Okay, so this one, I'm not saying it will exactly behave as an amplifier. It will behave, it may change its behavior depending on the frequency or the capacitor values that you are applying. Okay, so the start of the question has to be with virtual ground concept. So whichever feedback is stronger, the circuit behaves in with that. Okay, so suppose if the positive feedback is stronger, it will start oscillating. If the negative feedback is stronger, it will not. So basically, when it will it oscillate? It will oscillate when it satisfies the Barkhausen criteria, right? 360 degree. So if both the feedback together are making 360, this will oscillate. If they are not able to make 360, it will not. Suppose the gain of this circuit is asked. Then what will be the gain of this circuit? So the gain of the circuit is nothing but 1 plus RF by R1. RF by R, right? So this is R, RF, and this is R. Why it is 1 plus RF by R? Because input is applied to the positive terminal, right? And this 1 plus RF by R, it is obtained with virtual ground concept. Obtained with virtual ground concept, which is applied only in negative feedback, and this gain is actually the DC gain. Okay, DC gain means omega is 0. So if omega is 0, then this is open. Okay, and you got a relationship. So you got the gain of the circuit. Now this gain cannot change. Okay, now whatever, now your doubt may be that, okay, if the capacitor is open, then how I am writing this second equation? Because the capacitor is open, right? So here what we are doing is, whenever capacitor, we are talking about a capacitor, that means we are involving frequency now. So whatever the DC gain is, how is normally the DC gain? If you remember, for a low pass filter, high pass filter, what happens? It is like this, right? So the DC gain is omega equal to 0, the DC gain is that, and till some frequency, which is the cutoff frequency, the DC gain will stay. Okay, so within that cutoff frequency, if your capacitor value and your frequency value is your capacitor value is such that the cutoff frequency is within this range, wherever the DC gain is there, so you can apply that formula now. You understand? Now you can apply this, you can use this relationship. Okay, So till that point you can use that relationship. Okay, so you can take the capacitor into picture, use that relationship, because the DC gain is valid in there. Okay, so now after a point, it may happen that after a point that this circuit no longer behaves as a low pass. So this is basically a low pass filter circuit, you see. This is an R and a C, and the 1 nanofarad capacitor, normally these are used for, you can say, like noise grounding or high pass filtering kind of an action these will have. Okay, so this is nothing. Don't care about that 1 nanofarad much. So this is basically like a, so this one is basically a low pass filter, and this cap also aids to this low pass filter action. Okay, so this is basically a low pass filter designed, a non-inverting low pass filter. Okay, this is not an oscillator circuit. Okay, so these kind of capacitors, so let me show you. So these kind of capacitors are normally attached for low pass filtering action. So whenever there is very high pass filtering, whenever suppose you are designing some PCB, so the PCB routes will have noises. Okay, the route of the PCB will have noises. Okay, and those noises will then cause your op-amp output to be unstable. Okay, so therefore we add these kind of additional capacitors, which are very small value capacitors, very small value. So this is 0.1 nano, right? So exactly, very small value capacitors are added so that those high frequency oscillations are grounded. Those high frequency oscillations normally come from power supply noise, and the power supply noise is nothing but the noise from the PCB tracks. Okay, and the supply from wherever you are taking. So even if your supply is regulated, the noise, the PCB tracks add up to the noise, and therefore these kind of caps are used in a feedback, with your feedback resistors or something, to cause those kind of actions. Okay, but if those capacitor values are not carefully monitored, they cannot aid to those stability. They can also cause oscillations. Okay, so let me go to the second problem. Yes, this was asked in GATE 2020, probably a 1 mark question. Okay, so Chandrasekhar, is the doubt clear?
Yes, ma'am.
Okay, so one more way of thinking it is that in the question, if there is no other information available, then you can actually not apply anything. Suppose if you saw this question in exam and you are getting confused which type of feedback it is, just try to see if there is any comparator type of question is there or not. Like if it is a comparator kind of question, so no. If it is an oscillator kind of question, is omega involved? No, there was no other information given. So from that point of view also, you can think that okay, I cannot apply anything else but a virtual ground concept, and then I will just solve it. So that is not a good way of thinking, but in a competitive exam where you only have to write the answer, that can be a way of thinking that leads you to get marks. Okay, but right now you should understand the concept and understand everything properly in that question. You should not think in that way. Okay, so now in this circuit all the components are ideal. If Vi is plus 2 volts, the current so I naught sourced by the op-amp is dash. So now if we try to solve this question quickly, okay, so Vi is 2 volts. You see this is a negative feedback op-amp, so no comparator action is there. Okay, negative feedback op-amp, you can apply big virtual ground concept. So this is also 2 volts, right? So if this is 2 volts, then you can find V naught, right? So if this is 2 volts, that means this current is 2 milliampere. If this current is 2 milliampere, what goes inside the op-amp is 0. So this is in this direction 2 milliampere. If this current is 2 milliampere in this direction, what is your V naught? V naught is 4 volts. You cannot find V naught through this node. You have to find V naught by applying KCL or KCL at this node, or a KVL equation. So I had applied the KVL in this loop. Okay, so V naught is 4 volts. So once V naught is 4 volts, what is the current here? 4 milliampere. Right? What is the current here? Okay, so now if this is 4, this is 2, then I naught will be 6. Okay, so let me redo this. We applied a plus 2 volts here. This is ground. This is 10. This is V naught 1K. It's correct, right? Oh, sorry, this is 1K. You can directly find V naught with, because this is a non-inverting amplifier, so directly you can write V naught as 1 plus 1 into 2, so 4 volts. Is this fine? So no need to apply this loop which I was talking about. No need to solve it. This is 1 plus RF. So if this is RF, this is R. So 1 plus RF by R. Since this is a non-inverting amplifier, okay, and 1 plus RF by R into Vin is V out, right? So 1 plus 1 into 2 is 4 volts. So this is V out is 4 volts here. So you are asked I naught, right? So if 4 volts is this, so in this direction your current will be 4 milliamperes. Right? Now the question is which direction this current will be. This current. This will be in which direction? So this is higher, 4 volts. This one is 2 volts. So then current is in which direction? So if I take this to be the current direction I, or let me take this to be correct direction I, okay. So let us solve the equation. I is nothing but minus 2. That means the direction of current has to be opposite to what I have drawn. So this is 2 milliampere. So if this is 2 milliampere upward side, this is 4 milliampere. That means the op-amp is supplying 6 milliamperes. Okay. Be careful of this. So one silly mistake that can happen in this question is this only. Either the answer is 2 or the answer is 6. Any doubts? Okay. So then let's go to the next one. Yeah. So this is also a simple question, but I deliberately took it. Okay, to show you how you can solve this question very easily. Okay. So now when you see this question, how will you do it? First is you need VB, because if you have VB, you can apply virtual ground concept and you get VA. Correct? So now what will happen? What is VB? So no need of applying anything. What is happening? See, V, okay, sorry, VB is here, right? So now you see the current going inside the op amp is 0. The current going Inside the op-amp is 0. That means this is nothing but a serial circuit. Serially 20 kilo ohms are added, present. So that means it is nothing but just like this. So voltage division you can apply 20k, 20k, 10 volts. So what will be the voltage here? 5 volts. That's it. Okay. So VB is 5 volts. So no need of applying KCL here. Okay. Now if VB is 5 volts, from virtual ground concept, VA is also 5 volts. Right. Now if VA is 5 volts, we have 5 volts here as well in the input. So if both are 5 volts, will there be any current through 100k? There will be no current through 100 kilo ohm resistor. So here there is 0 ampere, because both are, the resistor is basically connected between 5 volts, right? And input, the input current of op amp is 0, ideal op amp, you know that. So if this is 0, this is 0, that means the entire current is, what is this? The entire current is what? So what is this current? This is 0, right? KCL has to be satisfied, na? So this is also 0. So if both these currents are 0, then this third branch current is also 0, and therefore V naught is 5 volts. Okay, so this question I deliberately took just for its approach. Otherwise, what we would have done, we will find VB first. How we will find VB? We will do VB minus 10 by 20 plus VB by 20 equals to 0, and then we find VB from here. And then we do VA minus 5 by 100 plus VA minus V naught by 1000 equals to 0, and then you put VA equals to VB and then you solve. This is also a cool approach, no problem. But you can just look into the question and solve it, right? And this saves you time. So this is the approach you will have to learn. And you will learn this slowly by practice only, okay? So if you are not comfortable with it, you simply solve KCL equations. But if you are comfortable, then you should solve in that way. That if it is connected, I know the current inside the op amp is 0. So this voltage is nothing but 5 volts, because 10 volts is equally divided between 20 kilo ohms. If this is 5, then this is 5, and it is connected between two 5 volts. So if it is connected between two 5 volts, this is 0. This current is already 0, so that means this is 0. If this is 0, then this 5 volt is what we notice. That's it. Now suppose if instead of 5, this was 10 volts. This was also 10 volts. Okay. So then you have 5 volts here, 10 volts here. So 10 minus 5 is 5. 5 by 100. So this is 5 by 100 milliamperes. If this is 5 by 100 milliamperes, this is 5 by 100 milliamperes. And now again you have 5 by 100 into 1000 plus V naught is 0. So you have V naught equals to 5 minus 50, which is minus 45 volts. Okay, but suppose here plus VCC is given as plus 15 minus 15. Therefore, your answer will be minus 15 volts. Is this clear, or should I repeat? I just told you a second possibility of the problem. Okay, second possibility of the problem. Always remember to check the saturation levels, plus VCC and minus VCC of op amp. If it is given, then you have to be more careful. Okay, so if this simple problem is clear, then let's see what the next problem I have. Okay. Okay. So determine pass band gain and cutoff frequency of filter shown below. The value of capacitance shown is C1 equals to 0.01 microfarad. So please try this one. So what kind of circuit is this? Can you please write in the chat box what kind of a circuit it is? It is written it is a filter. So what kind of a filter is this? Anyone? What kind of a filter is this? Chandrasekhar?
Band pass, ma'am.
Okay, one is band pass. Another, anyone else? Okay. So whenever you have to recognize a filter, it is very simple. Okay. All you have to do is to put omega equals to 0, omega equals to infinity. That's it. So what do we mean by omega 0, omega infinity? So this cap, this reactance is Xc, and this can be written as 1 by omega C, right? So the reactance that this capacitor is going to show the signal. Okay, so there is a input signal, and it will show some kind of something it will show, right? C, right? So there is a resistor, suppose. So this resistor is showing a resistance to this signal. So similar way, this capacitor which is there in this circuit, this capacitor that is there in the circuit, it is showing some capacitance, some reactance. Okay, so this reactance is given by 1 by omega C. Now if you put omega as 0, your reactance is infinity, and if you put omega as infinity, your reactance is 0. So at omega equals to 0, if reactance is infinity, that means this cap is open circuit, open, there is nothing here. That means this signal, entire signal can enter the op-amp. This circuit in omega equals to 0 is as good as this circuit. It is the same as this circuit. Now if I would have directly given you this, you will know what it is. It is a non-inverting amplifier. And it is same because the cap is now open. When? At DC. And also at very low frequencies, it will be open. It will reach at some frequency where it will not be open. It will behave like a closed one. How? Because the capacitor value will decide that. So Xc is equals to 1 by omega C. Now suppose I put omega as some 100 Hertz, 200 Hertz I am putting, and cap value is also some value is there. So when these two things multiply and the Xc value, suppose it is coming around 1K or something, 1 kilo ohm or something, then the capacitor will start showing that 1K to this signal, and therefore this signal is now going to get attenuated. So if this is 1K, then this signal will be Vin by 2. Now the input is Vin by 2. I hope you are understanding. So how to check the filter? If this is open, if all the signal is going inside, and at high frequency, this is closed. So if this is closed, then this is ground. And if this is ground, then this is 0 volts and your output is 0 volt. That means this is a low pass filter. At infinity, it will make your output 0. And at low frequency, it will give you the full output. And at some frequency, after some frequency, it starts drooping. That frequency is decided by the value of this resistor and capacitor, which is nothing but omega equals to 1 by RC. So this is that R and this is that C. That is the frequency. Okay. So whenever you see, another thing is, whenever you see R and C in series and the output is taken from the capacitor. So this is actually taken from the capacitor, right? This is a low pass filter. Whenever you see R and C circuit, this is also an R and C circuit. There is no difference between both the circuits, right? Except that now the input is applied to the capacitor directly and output is taken from the resistor. Okay, so output is between resistor and this thing. So this is a high pass filter. You can check yourself and see the way I have told you. So omega equals to 0, cap is open, this capacitor I am talking about, this one. So capacitor is open, so output will be what? So if this cap is open, there is zero current here, right? From V in. So if there is zero current, this is nothing but 0 volts, right? And if the cap is closed, then the entire signal is V out equals to V in. So this is a high pass filter. This cutoff frequency is called as FL, lower cutoff frequency, because in the high pass filter, from the lower cutoff frequency, it will start showing you the output. And in the low pass filter, what we define is a higher cutoff frequency, because the frequency occurs at a higher point, FH. After that, it droops down. And therefore, in a band pass filter, what you see is something like this. FL, FH. Okay. So, if you see in this Opamp question, if you see, this is nothing but a R and C. Nothing but a R and C. So, this is a low pass filter. Okay. Now, let's come to the question. What it is saying. The pass band and cutoff frequency. Pass band gain. So, what is the pass band gain? So, as I mentioned, at omega equals to 0, the cap will be open. The input will directly go to the positive terminal. Right? Input will directly go to the positive terminal. And if the input directly goes to the positive terminal, then this is what? This is what kind of configuration? Non-inverting amplifier. Right? So, therefore, your gain is, passband gain is 1 plus 10 upon 10, which is 2. Now, be careful, if they have asked you in dB, you have to do 20 log 2, which I think is 6 dB. Okay? If they ask in dB. If they are not asking in dB, then your answer is either, your answer is 2. So, one more thing they can confuse is, they can give you either 2 or minus 2. Or they can give you 2 or minus 1 in option. Why? Because if that is an inverting amplifier, if it had been an inverting amplifier, your answer would be minus 1. So if you don't see it carefully, that which terminal is accepting the input, if you are not seeing that carefully, you will end up getting a wrong answer. Am I clear or am I too fast? Okay. So this was our...
What is pass band gain?
Okay. So since this is a low pass filter, this is just nothing but a notation. So since this is a low pass filter like this, the pass band is this, right? So this is the gain they are talking about, pass band gain, which is nothing but the DC gain or the low pass filter gain. Anything they can write, because the gain is only in that part. After that, it is attenuation. Okay. So now easily you could have found out, right? You know this is an inverting non-inverting amplifier, because the cap will be open in during this thing. The cap will be open during DC part, or till the point it reaches the cutoff frequency. The cap will offer a very low reactance, and therefore the gain is directly 1 plus 10 by 10, which is nothing but 2 plus 2, right? Now, what is the frequency they have asked, right? What is the, and the cutoff frequency if C is 0.01 microfarad. So, C is 0.01 microfarad. What is the frequency? 1 by RC. Or so depending on whatever the unit they have given you. If they have given you radian per second, you will do omega. If they have given you hertz, you will do F, 1 by 2 pi RC. So this answer will be in hertz, this answer will be in radian per second. I'm not solving it, okay? So is this question clear? This question could have again come like in this way. Now this is what? High pass filter, right? But the pass gain is the same, 2, and the omega is also the same. Whatever you are getting, say we are getting 1k. So omega is 1 radian per second. Let us say, okay, I'm not sure. So let us say f is, I don't know what answer it will come. So f is equals to 1k kilohertz. So let's see. So in this case, your output will be in this manner and this will be 1 kilohertz. And the cutoff frequency is nothing but that frequency where your gain is 0.707 times or 3 dB down from DC gain. 0.707 times A, where A is this. Or if you have taken it as 20 log A, then this will be 20 log A minus 3 dB. Okay, just have a look into it. So had this circuit be this, it will be a high pass filter. Now it can be a band pass filter also. So how will you recognize a band pass filter? So in band pass filter, what will happen when you give omega equals to 0, at that time also you will get 0 output. And when you get omega equals to infinity, at that time also you will get 0. That means the signal lies somewhere between the frequencies. Therefore, at omega equals to 0, it is 0, and omega equals to infinity also it is 0. So this is a band pass filter. Yes, Chandrasekhar.
Ma'am, in this graph, we can see at omega is equal to 0, the gain is 0. And you are saying that pass gain is 2 for a high pass filter.
So what will be the pass gain, Chandrasekhar? What do you mean by the pass gain? So you are actually getting confused because I mentioned the term DC gain. So the DC gain is actually only applicable for low pass filters, because we are talking about omega equals to 0. And only in these kind of thing we talk about DC gain. We don't talk about DC gain for high pass filter. And also in normal amplifiers, normally the amplifiers are not like normal amplifier. When you talk about, if you remember, we have this kind of a waveform, right? For BJT, MOSFET, everything we have this kind of waveform, right? For amplifiers. So this is nothing but, we draw it like a band pass filter, but this is nothing but the same. It is kind of a low pass filter only. Okay, so here the concept of DC gain is there. But when I say pass band gain, I can apply the pass band gain term to high pass filter as well, because it is just the gain which the filter shows when it passes the signal. So at high pass filter, it is actually passing the signal, and therefore you can say this is the pass band gain. Okay, but only for low pass filter or band pass filter you can say at omega equals to 0. Not actually technically at with band pass filters, but especially for BJT, MOSFETs, and even with Opamps, the normal behavior of the circuit. So suppose I say I have this Opamp, right? So this don't have any this is not having any caps, right, Chandrasekhar? But if this Opamp is a non-ideal Opamp, then what will its frequency response look like? It will look like this. Okay, so every time remember, normal circuits, they will behave very nicely in low frequencies and they will mess up at high frequencies. So normal circuits, these amplifiers, they are all good behavior candidates at low frequencies. And why is that? Parasitics. Because everything here is conducting. That means if everything here is conducting, then two conducting plates will form nothing but a cap, right? A capacitor will form between two conducting plates. It can be anywhere. And therefore in BJTs, Opamp is nothing but what? It is made with BJTs only, right? Or MOSFETs. So in BJTs, all these parasitics keep on coming, right? And therefore when we draw the amplifier profile of a BJT, we draw it like this and we say that, you know what? This is the low frequency caps doing. This is because the low frequency caps we are getting 0, and here because of the high frequency parasitic caps we get 0, and this is because of the DC coupling caps we get 0, and in between we get the output. But if you do it in oscilloscope, you will see this value is so small that it can be approximated as a low pass filter action only. Is the doubt clear, Chandrasekhar?
Ma'am, whenever we will be finding pass band gain, so we will calculate at omega is equal to 0.
Yeah, so whenever they have asked you a pass band gain like this, you will be doing in this way only. Okay, they will normally give you in a low pass filter only. Okay, so if it is a high pass filter, they will ask you the question like what is the pass band gain at higher frequencies or something like that, they will ask you.
Okay, ma'am.
Okay. Okay. So see, basically when I was telling you the DC concept, so it's a good point actually. You got a very well confusion. So if it is a high pass filter, so as I was mentioning, right, Chandrasekhar, this is Vin, right? And if this is like this, right? So now at omega equals to infinity, what will happen? The signal is going to get in, right? So now what was DC gain for your low pass filter? It is the passband gain for your high pass filter. I cannot call it DC because obviously I am getting it at some other frequency. You understand?
Yes, ma'am. Yes, ma'am.
It is clear, right? Don't get confused with the terminology. Is this fine?
Yes, ma'am.
Or can you explain it back to me?
Yes, ma'am. For a low pass filter, for omega is equal to 0, we are calculating pass band gain. And for high pass filter at omega is equal to infinite.
Right.
Or any other other than 0.
Right.
Yes, ma'am.
Yeah. And if it is confusing to you, simply draw the circuit and you check it. Okay. Okay. So it is just the framing of the question that differs. Okay. So good point. Yes. So I have another question which again relates to the kind of thing we do in control systems and network analysis in your sinusoidal response. Okay, so there is one chapter with transient analysis and sinusoidal steady state responses, sinusoidal responses. So what will we do in these kind of problems? Okay, so whenever your option is in this way, sine t minus 45 like this in terms of sine, what do? The input is sine t, right? And here 1k 1 millifarad, and then 10k and 10k is connected. It's a similar circuit as we saw. It's just a low pass filter, right? So what will be your transfer function? What will be your transfer function? So you can actually derive it also, right? So let me derive it. So Vx minus sine t upon 1k plus Vx, I am simply writing, okay, let me write SC for now. Okay, let me write SC for now equals to 0. Okay, so now what will be Vx? Vx is nothing but sine t upon 1 plus SC. Okay, now this Vx is, by virtual ground concept, is the same Vx here, and therefore what is V out Vx value here? What will it be? We could have done it in another way also. We need not write it this equation, right? How? So if this point is Vx, we said this point is Vx, right? So this is as good as this. So this is Vx, this is 10k, this is 10k. It is nothing but a non-inverting amplifier. Right? So I need not write a KCL equation. I can directly write V out as 1 plus 10 by 10 into Vx, right? Which is 2Vx. So always remember, look into this terminal, okay? Node, input node of the op-amp. Anything can be connected in this side. It can be a black box. This can be a black box. Okay, so here if it is Vx, V out's relationship with Vx is 2 times Vx. That's it. You need not write any KCL equations. Okay, so now I hope you have understood this, because now we are completely doing non-inverting, inverting again and again. So now if this is Vx, then this is nothing but what? V out by 2 equals to sine t upon 1 plus Sc. Now V out equals to 2 times sine t by. Now what is 1 plus Sc? Did I miss something? Yes, so here you see this was 1k, right? This was 1k. So I had actually, since it is 1k, we are not seeing the R term here. Okay, or otherwise you will see a term R, capital R, because RC is your omega. Okay, so anyways, so this is 1 plus Sc. So now what will you do? You will write it in, since this is the format of your objective answer type, what will you do? You will write it in the form of a polar coordinate. So sine t upon 1 plus j omega c. Okay, now what is omega? Omega is 1 by RC. You know that. What is R? It is 1k, and what is C? It is 1 millifarad. So that means this is 1 hertz. 1k into 1 millifarad. Everything will cancel out. So 1 hertz. Okay. So now you write it in polar form. 2 sine t upon under root 1 plus omega square c square. And what is the angle? Tan inverse omega c by 1. I hope you know this. This is nothing but complex numbers representation. Okay. Now omega you know it is 1. C you know it is 1 millifarad. So 2 times sine t upon under root 1 plus 10 to the power minus 6 angle tan inverse 10 to the power minus 3. Okay. So now what this will be? So let me find out what it is. Tan inverse this will be tan inverse of 10 to the power minus 3 degrees. Okay, it is showing me some other value. So I think it is near around 0. So this is t, and this will be a very small value. So this is nothing but 1 angle 0. So the answer is 2 sine t. Okay. So is this clear? You have to first arrive at the, and I did this because my options that were given were in this form. Okay, so please check if I have done any silly mistakes in between. If I haven't done any kind of silly mistakes, then this is what your answer should be. Okay, and one more thing, suppose this was not let's say this was 1 kilo ohm in place of 1 kilo ohm and 1 millifarad, it was 1 ohm and 1 farad. In that case, you will see that you will arrive in something like this. Right, and here suppose omega is 1 hertz and C is 1 farad. Okay, so what you will get? You will get 2 by root 2 sine t, and there is an angle of, so this is minus because it was in denominator, you have taken it to numerator, so this is a minus angle, negative angle, omega c. So tan inverse 1, and what will be tan inverse 1? It will be 45 degree. So root 2 sine t minus 45 degree, and this is the bracket. Okay, so basically this is nothing but a kind of representation. So you did not enter into Laplace transform and stuff like that for solving this question. You can simply write it in this polar coordinate representation and you can solve it. Okay, this normally we do when we are doing control systems, second order analysis. We write the output expression in this way. Okay, okay, so with this I will wrap it up. Okay, please, if you have any doubt, you can send me sometime else. Okay, then you can leave the meeting if you don't have any other doubts. One second, I think this question was solved wrong because I have left R value. So basically when I had calculated omega, I have taken R, but here the unit is 1 kilo ohms, right? So this cap, it will get multiplied to 10 to the power minus 3 here. So this cap will get multiplied. Yes, so this was a good thing. This is a mistake that can happen. And here also it will get multiplied to 10 to the power 6. So the answer will be root 2 sine t minus 45 degrees. Okay, this will be the answer. So let me just once again quickly solve this and let me tell you where was it wrong. So when I had applied this KCL equation, I had just considered it as 1 kilo ohm. So 1 kilo ohm, I just wrote it as 1, right? I did not write the unit. So whenever you do things like this, then that would mean that everything else in the circuit you will have to maintain in the same way. So cap also, it is given 1 millifarad, you will have to maintain it as 1. Okay, so therefore when I am doing this, omega is 1 already, and therefore when I am putting these values, I should not put C as 10 to the power minus 3, I should put C as 1. Because already R is taken care of. This transfer function should have R, the value R should have been there in this transfer function, but earlier only while writing KCL I had substituted R with 1 kilo ohms and I had written it as 1. So if I write 1 kilo ohm as 1 millifarad should also be written as 1, right? So therefore this is nothing but 1 plus 1 angle tan inverse 1 into 1, which is nothing but root 2 sine t minus 45. The other way of writing this will be if I write directly from this transfer function, which is 2 sine t by 1 plus j omega rc, and you can see it is sine t by under root 1 plus omega square r square c square, and tan inverse angle is tan inverse omega rc by 1. Okay, this one is this omega rc1 is nothing but this one. Don't confuse. Okay, so yeah, this is the mess up I had done by mistake. So if this is R, then this will be R. Okay, so I hope it is clear. Please note down this question and try to solve it in your own, you will understand. Okay,
Ma'am,
Yes.
ma'am, you were telling something Burke's criteria. What is that?
Oh, so you can. There is the criteria an amplifier needs to satisfy to work as an oscillator. Okay, so for that, your feedback ratio, so your A beta should be 1. Okay, and the angle of your feedback, that the angle should be either 0 degrees or 360 degrees. So you go and check it more. Okay, so it is a long topic, I cannot explain it here.